So conformation means rotation, and the rotation happens around two carbons, and these carbons they have to be connected by a sigma bond. The two carbons cannot be connected by a double bond. There is no rotation around a carbon double bond carbon in there. With carbon double bond carbons, we have different orientation of the molecules. So if you have a carbon double bond carbon, the orientation of the molecules can be either trans or they can be cis. So the molecules around the double bond can either be arranged on the same side, and in this case they are cis, or they are arranged on opposite sides and they can be trans. There is no rotation between cis and the trans. So you cannot say that I do a rotation of the trans and I get cis. This is not the way to do it. In order to go from cis to trans, what you need to do is break the double bond. So you have to break the pi bond, rotate the carbon, and then you go from trans to cis. So there is no free rotation around a double bond. The free rotation only happens around a carbon single bond carbon, around a sigma bond in there. You can rotate clockwise or counterclockwise. When you do the rotation, normally you fix a carbon and you rotate the other. It doesn't matter which carbon you fix and which carbon you rotate. So, for example, if I am looking down the side, you can view the molecule at any angle you want. So, if I am looking down the side in here, the first thing that I'm going to see is this carbon. So, this carbon is going to be the front carbon, and the one at the back is the one that I am not going to see. We prefer to fix the carbon that is at the back always and rotate the carbon that you are seeing, which is the carbon in front. You can fix the carbon in the front, rotate the carbon at the back. This is not a problem. On the other hand, I can also view the molecule from the side. And again, you can view it at any angle in there. Then in this case, this carbon is going to be the one at the front, and the other one is going to be at the back. And normally you fix the one at the back and you rotate the carbon that is in front. There are two different types of conformations around a carbon single bond carbon. So again, conformation is whenever you rotate around two carbons. So no matter how long your chain is, let's say for example, I have a chain with X number of carbons, all what you need to do is pick two carbons, any two carbons, and do the rotation around. They can be these two carbons or these two carbons or these two carbons. They can be any two carbons in there. So any two carbons and do the rotation around. When you do the rotation, you end up getting two different types of conformations. There's the eclipse and there is the staggered. To represent the eclipse and the staggered, you represent them by lines in there, and this is the molecular model for them. So the definition for the eclipse is whenever all the bonds align, meaning that if you're viewing the molecule from the side, you're not going to see the carbon at the back because all the bonds align, and the angle between those bonds, we call it a dihedral angle, and it is a 0 degrees. To represent the sawhorse, simply look at your molecular model and translate it into a sawhorse as you see it, draw it. So you see a hydrogen pointing up this way, just go ahead and draw it. This is the first carbon that you see. The second, you don't see it because those two, they align with each other. And then you have one hydrogen on the right, the other hydrogen on the left. Normally the hydrogens on the right, these are the ones in front. And the ones at the left, these are the ones at the back. So these two are going to be at the back and these two are going to be in front. This is a sawhorse representation of the eclipse. I can do a rotation of 180 degrees for both carbons, and now I'm going to end up having these two hydrogens down. Still they are aligning. So still here, I have my bonds between those two hydrogens. This is a 0 dihedral angle. The bonds between these, or the angle between those two hydrogens, is a 0 degree angle. and between those two hydrogens is a 0 degree angle. So this is again a representation of the Sawhorse eclipse. Whether you represent it this way or this way, this is an eclipse Sawhorse conformation, and these two are going to be the same. Staggered conformation is when you fix one carbon in the eclipse and rotate the other carbon 60 degrees. So when you rotate this carbon 60 degrees, this means that now this hydrogen here is gonna go ahead and end up being down there. So your dihedral angle now between the bonds, between those two bonds here, it's going to be 60 degrees. And between those two bonds here, it's going to be a 60 degrees. To represent the staggered conformation, we represent it as a sawhorse. And these are the two ways of representing it. By simply viewing the molecule from the side along this line, then this carbon is going to be the one which is pointing at you. So you see it. This is the first carbon that you see. And the one which is at the back, this we expect that you're not going to be seeing that because this carbon is going to be hiding it. So you won't be able to see this carbon. But definitely you're going to see its bonds in there. As you see it in the molecular model, you go ahead and you draw it. So you have your hydrogen pointing down. This is the hydrogen pointing down. And then you have two hydrogens on the side. These are the two hydrogens on the side. Now, whatever group is to the right, normally these are the ones that are in front. This is important because if you want to change this into a 3D model, then you want to know where are your groups that are pointing in front and where are your groups that are behind. Hydrogens on the other side, on the left, these are at the back. So these are the ones that are behind. And then these two hydrogens here, they are in play. There are two conformations for ethane that exist, the staggered and the eclipse conformation. And to go from the eclipse to staggered or staggered to eclipse, you fix one carbon, you rotate the other carbon, and the rotation has to be 60 degrees. So you rotate, every time you rotate the 60 degree, you go from eclipse to staggered, staggered to eclipse, and so on. Between those two, the maximum, the one which is the most stable is the staggered conformation, because as you can see, the bonds are not aligned. There is an angle between them, and that angle will provide the separation needed for less interaction between the groups around the carbon. Notice that these two groups here are the farthest away apart. These are the 180 degrees apart. So that makes the structure more stable compared to the eclipse conformation where all the bonds are aligned. All the bonds are 0 degree dihedral angle between them. This means that there is a lot of repulsion going on between the groups of the ethane. Even though these groups are hydrogens, and we know that hydrogens are small molecules, but these hydrogens are eclipsing each other, meaning that there is no angle between them. They are right on top of each other in there, so they're going to repel each other. And we know that as the energy increases, so we know as the energy increases, as the stability is going to decrease. Stability is going to decrease. The first way is so other than the sawhorse representation that represents the eclipse and the staggered, I can also represent the conformation between two carbons of the alkane by a Newman projection. Newman projection is still going to have the eclipse and the staggered representation in there, but it's not going to be a sawhorse anymore. So let's go ahead and have an example. Okay, here draw all the Newman projections of a butane. Whenever you are given an organic molecule, please go ahead and draw it. You can draw it in a skeletal form, or you can draw it in a condensed form, whatever you want, or in a structural form. Whatever method you want to use, go ahead and use it. I'm just going to go ahead and draw that in a skeletal form. Okay, so this is butane in there. Number according to the IUPAC rule here, it doesn't matter on which sides I start numbering. So I need my conformation or to draw the Newman projection along carbons 2 and 3. So this is carbon 2 and this is carbon 3 in here. If I start numbering from the side, this means that I am viewing the molecule along this line here. So along carbons 2 and 3. So the first thing that I would be seeing is carbon number 2. To draw the Newman projection, simply the first carbon that you see is represented by a dot. And the second carbon that is adjacent to it, that you're drawing the Newman projection around, is represented by a circle. Okay? So here, when I look at the dot and the circle, I know that the Newman projection is between those two carbons in there. I need to number that dot, this is carbon number 2, and number the circle, this is carbon number 3. Then I'm going to go ahead and draw the substituents between carbons 2 and 3. The substituents on carbon number 2 are 2 hydrogens and a CH3. Now, I don't care about carbon number 3 because I already drew it and I already represented it by a circle. And this means that carbon 2 is connected to 3. So only I care about whatever is connected to carbon number 2 other than carbon number 3. I'm going to do the same thing for carbon number 3. So for carbon number 3, I have 2 hydrogens here and I have a CH3. Now, it is always better if you have a carbon chain to keep your carbon chain on the vertical line of the Newman projection. So starting with carbon number 2, I have my, as you see it, draw it. So I have my CH3 here pointing down like that. You see that? So I'm just going to go ahead and put my CH3 down. And then I have a hydrogen on the side, and then I have a hydrogen on the side. And this is going to be my CH3. Always start with the Newman projection, drawing the staggered conformation, and then rotate to get the eclipse conformation. On carbon number 3, I do have my CH3, so I'm just going to put my CH3 up, and then my 2 hydrogens. So as I mentioned, so these are my 2 hydrogens here on the 3. I just going to put them along the sides, and then you have your CH3 up. So see your line over there with the carbons, your carbon chain. Your carbon chain, it is better to be on the vertical line every time you start drawing the Newman projections. Now here, as you can see, I don't have any bonds aligning. The dihedral angle between those 2 bonds is 60 degrees. We know a full circle is a 60 degrees, so the dihedral angle between each of these lines is a 60 degrees. So if you go all the way, this is a 360 degree full rotation. Okay, here you go. Start with your, as we said, start with the carbon chain being on the vertical line every single time. You can do that. So bulky groups, make sure that your big groups here, the biggest groups I have in this structure are the 2 CH3s, just make them on the vertical line. So that whenever I want to look at this Newman projection, I know that this Newman projection is made up of 1, 2, 3 carbons, and then 4. This is a 4 carbon chain since the groups that are connected to the carbons are hydrogens on the sides. So this type of conformation here, we're going to call it an anti-conformation. It's anti because your large groups, which are the CH3s, are 180 degrees apart. Count, this is 60 times the 3, they are 180 degrees apart. So anti-conformation is whenever the large groups, they are 180 degrees apart. And that makes the conformation the most stable among all the conformations that we are going to draw. Now, once you draw your staggered conformation, so this is the anti-staggered conformation. Now we're going to go ahead and start rotating. So to rotate, we're going to fix one carbon, rotate the other carbon. I'm going to fix the carbon in front, rotate the carbon at the back. You can fix the carbon at the back, rotate the front, it really doesn't matter. But here I'm fixing the carbon in front. So whatever carbon you are fixing, just go ahead and draw it with the rest of the Newman projection. So I'm just going to go ahead and draw all the conformations here that includes that carbon being fixed. That will save me a lot of time. I know a full rotation is a 360 degrees. So I am doing 6 rotations in this case to reach the 360 degrees. So I'm going to end up having six of them. So since I am fixing this one, I'm just going to keep everything the same. Hydrogen, hydrogen. Okay. For all the conformations. Now I'm going to go ahead and rotate the carbon at the back, which is carbon number 3, 60 degrees every single time. So rotation of carbon number 3, 60 degrees is going to end up having this CH3 over here eclipsing this bond. So I'm going to end up having the CH3 here. It doesn't matter if you draw the CH3 on this side or if you draw it on the other side. It depends how are you viewing it. Are you viewing it from the top or from the bottom? So it really doesn't matter. Then this hydrogen here is going to move and eclipse this bond, and it's going to be another 60 degrees in there. And then this hydrogen is going to move and eclipse this bond, and you're going to end up having a 60 degrees. So now what we have is an eclipse conformation. So this is called an eclipse conformation. So you went from the anti, which is the most stable, to the eclipse. Now we're expecting the eclipse, since there is a zero dihedral angle between the bonds, the energy of the eclipse is going to be more than that of the staggered, the anti-staggered conformation. Go ahead and rotate another 60. So don't forget that we are fixing this carbon. So rotate another 60 degrees. This is not a 60. This is a hydrogen in there. So rotate another 60 degrees. Then this CH3 now is going to be staggered. So every time you do the rotation, you're going to end up going from staggered to eclipse, staggered to eclipse, staggered to eclipse, and so forth. You're going to have a hydrogen here and a hydrogen there. Rotation another 60 will end up getting you the fully eclipse now. Fully eclipse is whenever you have the biggest group in your projection, in your Newman projection. Those, they align with each other and they are 0 degrees apart. So see those two over here, they are 0 degrees. So this structure is called fully eclipse. This one here is going to be called staggered, and since the groups, they are 60 degrees apart, which are the CH3s, we're going to call this a gauche staggered. It's still staggered conformation. So we started with the anti, we did 60 degrees, we ended up getting the eclipse conformation. We did another 60 degrees, so do the rotation over here. Imagine this one, the back is being rotated. Now the CH3 is going to be here, this hydrogen is going to be here, this hydrogen is going to be there. You're going to end up getting the staggered, but this staggered is different than this staggered. Both are staggered, but this one has its bulky groups or biggie groups. They are 180 degrees apart, so they won't interact at all. But here, the groups are 60 degrees, so you are bringing them together. As you are bringing them closer together, as the energy between them, repulsion energy, it's going to increase. Here we call it a steric interaction. It's a steric. Steric is a term that we use whenever we have big groups that are approaching each other. So this is a steric interaction here, and that steric interaction is called gauche. If you have two groups that are close to each other, they are exactly 60 degrees apart. So here you have gauche, staggered, and then whenever you're big groups are 0 degrees apart. They align with each other. We're going to call this fully eclipsed. Let's move on. Now go ahead and rotate another 60 degrees. Rotation another 60 degrees is going to end up having our CH3 now being here. We're going to go back to the gauche. So see, this is again gauche, staggered. And with the gauche staggered, let me highlight here. So see this one? This one is a gauche staggered. And this one, let's finish the structure. And this one is a gauche staggered at the same time. So these two, I'm expecting them to have the same energy because the CH3s are 60 degrees apart, the CH3s are 60 degrees apart. Everything else is the same here and here. So these two are going to have the same energy conformations. Go ahead and rotate another 60 degrees. Then you're going to end up getting your eclipse conformation. This is a hydrogen and this is a hydrogen. And let's highlight because we have here two conformations that are again the same. This is the eclipse conformation. And I've passed by the eclipse before. This is the eclipse here. And this is the eclipse there. And these two have the same energy. And then if I go ahead and do a rotation of another 60 degrees, then I'm going to end up having my CH3 here, my hydrogen here, and my hydrogen there. So I'm going to end up getting my N-type. The energy diagram is the plot of the energy, potential energy, versus the dihedral angle. And to get the values of the dihedral angle, just pick any two groups on the Newman projection and go ahead and calculate their dihedral angle and see how close they are coming to each other. For example, here we picked those two CH3s because these are the ones that are different from the hydrogen. So we're starting with them 180 degrees apart, and this is the anti-conformation. And as we are doing a 60 degrees, so going 60 degrees now, going 60, they become 120 degrees. Becoming 120 degrees away from each other, this is called an eclipse conformation. So in each one of those, you either have staggered, you have eclipse, but there are different types of staggered, different types of eclipse based on how close the CH3s with respect to each other. So eclipses always are whenever the bonds are aligning with each other. And the staggered is always whenever you have a 60-degree angle in there between the bonds. There is a difference between the anti-staggered and the gauche staggered, as you can see. Anti-staggered is when your CH3s are 180 degrees apart. Gauche staggered is when your CH3s are 60 degrees apart. So you go from the staggered, eclipse, staggered, eclipse, staggered, eclipse, staggered. Okay, back to wherever you start. So for the eclipse here, I have my dihedral angle to be 120. Always the eclipse has a higher energy than that of the staggered because the bonds are eclipsing. Then you have your staggered conformation. Staggered here is the gauche. And the gauche is whenever your CH3s are 60 degrees apart. Do another 60 and then you end up getting your fully. Fully is the one that has the highest energy. The highest energy, why? Because your CH3s, these are the biggest group in your molecule, and these two CH3s, they are aligning with each other. This causes the Newman projection to have the highest energy in there and to have the least stability. And then you do another 60, you go back to the staggered. Now notice that the staggered here and there, these are having the same energy. They have the same energy because both they are gauche. All the interaction that I have here is the CH3 gauche interaction. Do another 60, you go with the eclipse. These two eclipse conformations, they have the same energy. So 2, 6 have the same energy here in this example. And then the final rotation is going to bring you back to wherever you started, which is the 180. So always I start with the 180 and I finish with the 180. Let's have another example. So considering the rotation around the highlighted bonds, draw the Newman projection of the most stable and the least stable conformation. This is 1, 2, 3, 4, and 5. Okay, so you have here 5 carbons. So let's go ahead and draw the 5 carbons in there. So you have your 5 carbons. 1, 2, 3, 4, and 5. And I'm drawing the Newman projection around carbons 1 and 2. Okay, I'm going to go ahead and view the molecule from this angle. So the first carbon that I'm going to see is carbon number 1. And the one that is behind is going to be the second carbon. So this is carbon 1 and this is carbon number 2. Put your hydrogens, please, if you are working with the skeletal form. So carbon number 1 has 3 hydrogens in there. It's up to me. I mean, you can draw it whatever you want. I'm just going to go ahead and draw a hydrogen pointing down and then 2 hydrogens here. So that is going to be carbon number 1. Okay, you could also draw carbon number 1 like that. So you could draw a hydrogen pointing up and the 2 hydrogens pointing down. After all, you are doing the rotation in there. So you are rotating around this carbon. So it really doesn't matter. These two are going to be the same. Okay. So the second carbon, I have 2 hydrogens. And I have my R group in there. See the R group, how many carbons does it have? So for the R group, it has 1, 2, 3 carbons. And then on carbon number 2, I have a hydrogen and then I have another hydrogen. So remember what I said, that the longest carbon chain, make it vertical, make it on the vertical line. So on the vertical line here, I'm going to end up having my 3 carbons. So I'm going to end up having my CH2, my CH2, and my CH3. CH3 is at the end, so don't put the CH3 here. It is at the end. If you put it here, then the carbon is going to end up having 5 bonds. So you have your 3 carbons, your propyl, and then you have the 2 hydrogens on carbon number 2. Hydrogen here and the hydrogen there. Since I have all hydrogens in there, no matter how I rotate, so with the stagger, they are going to all be the same, because having rotating this 120, you know, to go from stagger to staggered, you rotate 120. From stagger to eclipse, you rotate a 60, because this is a 60 plus 60. So going from stagger to stagger, so whether the CH3, the propyl being here or being here or being here, it's all going to be the same. And this is going to end up to be the least or the most stable. It's the least energy. So it's going to be the most stable conformation. Now we're going to go ahead and do the rotation of 60 degrees to get the eclipse. When you do the rotation, you do it in one direction. One direction. You can rotate it clockwise, or you can rotate counterclockwise, whatever you want. You can rotate this side or to the other side. Normally, I like to rotate clockwise. Then in this case, rotation is going to be fixing one carbon. I'm going to fix the carbon in front and rotate the one at the back. And that is going to end up having my propyl group eclipsing. This is a CH2 and a CH3, eclipsing the bonds. And this is going to be my eclipse conformation. So this is going to be the staggered. And this is going to be the eclipse conformation. All other eclipse conformations, if you do the rotation of 120 degrees, then you're going to end up having this propyl here or this propyl here. And because the hydrogens are the same, all the eclipse conformations are going to have the same energy and they're going to be the same. So this is going to be the least stable conformation. Why it is the least stable conformation? It is the least stable conformation because every time I have groups that are eclipsing each other, they're gonna have some sort of interaction between each other and they're gonna repel each other. So here, the dihedral angle between them is 0. The dihedral angle between them 0 and the dihedral angle between them 0. So if I want to calculate the energy of this structure, there is a table with the value of the interaction, the energy interactions between those groups whenever they become eclipsing each other. So for I have over here hydrogen hydrogen eclipsing. So I have a hydrogen hydrogen eclipse, and I have two of them. I have two hydrogen hydrogen eclipse, and then I have a hydrogen and an R group, which is a propyl group here, eclipse. If I go ahead and look at the notes at the energy table, there's a special energy table in here. It's called energy strain table. It gives you the values in kilocalories per mole. There is another table in kilojoules per mole, but we're going to use the kilocalories per mole. Whenever hydrogens are eclipsing each other, this is the type of interaction. Then these two hydrogens, the type of strain between them, we call it a torsional. Torsional is whenever you have an eclipse conformation, you use this term. So torsional, whenever you have eclipse. Every time you have eclipse, you use the torsional term. Strain means that energy. So here you have torsional strain, which is torsional energy, but whenever you have two hydrogens that are eclipsing each other, if you have a hydrogen and an R group, regarding if it's a CH3 or if it is a bigger group than the CH3, we're just going to assume it's a CH3. So here in this example, it's a propyl group. It's not a CH3, but we're just going to assume it is a CH3. Unless I give you another value for the propyl in particular, then you can use it. Other than that, you just assume that it is a one carbon. And this is the energy value for it. If you have CH3s that are eclipsing each other, this is going to be a torsional strain. But on top of that, because the CH3s are big molecules or big groups compared to the hydrogen, we have also steric as well strain. So you have two types of strains, steric and torsional. And then you have the CH3 CH3 Gauche interaction. Whenever the CH3s approach each other in a 60-degree angle, then you're going to end up having no torsional anymore because Gauche exists in staggered and not in eclipse. So you're going to end up having just a steric strain. And steric strain has this value in here in the energy. Let's have an example. If you are given two Newman projections and you are calculating which one is higher in energy, the first thing that you do is check what type of Newman projections are they. For example, in this one, I am comparing the staggered with the eclipse. So the moment you see eclipse, we know that eclipse has a higher energy than that of the staggered without any calculation. If you're comparing two staggers together, then you would need to do the calculation, the energy calculation. So use the energy values in there. Look at the Newman projection and list down all the energy strain that you have with respect to the groups being close to each other. So here for the staggered, I only have a CH3 CH3 Gauche interaction, and that is going to be 0.9 kilocalories per mole. We call this energy of destabilization, by the way. Here I have two CH3 CH3 Gauche, so you multiply the 0.9 by 2. And then all what you need to do is just compare. So which one has a higher in energy? 1.8 is more than 0.9, then definitely this one is higher in energy. The question here says calculate the difference between the two conformations. You don't have to do this unless you are asked to calculate the difference. Then you take this value of destabilization, you subtract it from this value, but guys, make sure that your answer, this is the difference in energy, it's positive. So when you do the subtraction, you do it in absolute value. Let's have another example here. Considering the rotation around the highlighted bond, draw the Newman projection of the most and the least stable conformation. We're going to do exactly the same as we did. So in this case, you are going to locate your carbons. So we have these two carbons, and again, it's up to you. You can view your molecule or your structure either from this side over here. I'm just going to go ahead and view it from the side there, or you can view it from the other side. So I'm viewing it along this line. So whatever I'm going to see here is the first carbon that I'm going to see. This is carbon number 3, and this is carbon number 4. So it's going to be 1, 2, 3, and 4. So carbon number 3 is going to be the one in the front, and carbon number 4 is going to be at the back. So draw carbon number 3 in there. Carbon number 3 has the ethyl group pointing up like that. And then 2 hydrogens on carbon number 3. Just go ahead and draw them one on each side. And then carbon number 4 has the ethyl group. We agreed that, guys, draw the long carbon chain on the vertical line. And this is going to be ending up to be the most stable conformation because this one is going to be the anti. And then go ahead and do the rotation. We're going to do different rotations in there. The question is choose the least stable and the most stable. Now I know that the least stable is going to be the fully eclipse. So to achieve the fully eclipse conformation, I need to rotate 180 degrees, 60, 60, and 60, so that these two ethyl groups, they are fully eclipsed with respect to each other. For example, now let's say, for example, if we have this Newman projection molecule and we want to name it. Now, in order to name it, you cannot name it like this. So you have to change it, take it out of the Newman projection, and draw the skeletal representation of that molecule and name it from the skeletal representation. So in order to do this, I'm going to do this in steps. The first thing I'm going to do is I'm going to locate my 2 carbons in there. So this is going to be the first carbon, my 2 carbons around the Newman projection. So it's going to be this carbon and the carbon at the back. This is how I drew the Newman projection. So I'm going to go ahead and draw these 2 carbons in here. So it's going to be my first carbon, and this is going to be my second carbon at the back. Draw it as you see it in there. Now, on this carbon, I'm going to first draw it in terms of a condensed formula, and then I'm going to change the condensed into the skeleton formula in there. Just do it in steps at the beginning. After that, if you do a lot of practice, you will master that, so you can skip drawing the condensed and go all the way to the skeleton. So on this carbon here, what I have, so this is the carbon, what I have is exactly as you see it to draw it. So I'm taking out the circle and I am drawing the rest. And you have a CH2, CH2, CH3. You have all of the rest of your group here. We're going to go ahead and draw that. This is a CH2. I have 4 of them, and then a CH3, and then I have an ethyl group here. Okay, so I'm done from the carbon which is in front. I drew all of its carbons. Now the one at the back has the following. It has, and it's a propyl, so I'm just gonna draw the propyl, and the propyl is here. Let's use another color. So this is the propyl. And then I have my phenyl. Just going to put the phenyl in there. And then next to the phenyl, so I have my phenyl. And then I have my CH2, CH3. So I have my CH2 and I have my CH3 in there. Okay, let's go ahead and change this now into a skeletal form. So with the skeletal form, I'm just going to count my carbons and choose the longest carbon chain in there. It doesn't have to be the longest carbon chain at the beginning. So here you go. I'm just going to go ahead and choose the longest visual carbon chain that I can see. And the longest visual carbon chain that I can see is this one over here. So this is, let's count the carbons. It's 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I have 9 carbons. So draw your 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I drew that. Let's number them. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. On carbon number 7, I do have a propyl group. 3, 4, 5, 6, 7, 8, and 9. Carbon number 7, I have a propyl group, so go ahead and draw your propyl group, which is 3 carbons. And on carbon number 7 again, I have my phenyl, so draw your phenyl this way, you guys. If you number, you will not miss any of those substituents. You will have them all in. And then on carbon number 6, I do have my propyl and ethyl group. So on 6, I have a propyl group here. And then I have my ethyl group there. Here you go. So now, after you figure out your skeletal form, now you go ahead. I'm going to take out those numberings in there. Now you go ahead and you choose your longest carbon chain. Here you go. So you choose your longest carbon chain. Remember, when you are choosing the longest carbon chain, you want to take into consideration to have the maximum substituents in there. So I'm going to go this way. Here you go. I'm going to go this way. It's going to be my longest carbon chain and go down like that. This is a 3 carbon chain here versus a 2 carbon chain in there. And this will result of a 10 carbon chain. Starting to number from here because it's closer to the first substituent, which is the phenyl. It's going to be 1, 2, 3, 4. On 4, I have a phenyl. Let's highlight. And I have an ethyl. And on 5, I have a propyl. And I have an ethyl in there. So name that. This is 5, this is 6, 7, 8, 9, and 10. So this is decane. And then 4, I have phenyl, ethyl. So I have 2 ethyls in there. E comes first. So I do have a 4, 5 diethyl. This is going to be 4, 5. This is a comma. Diethyl. And then I have a phenyl and a propyl. Phenyl comes first. So it's going to be 4 phenyl alphabetically. 5 propyl. Please don't forget the dash and the commas between the word and the please don't forget the commas and the dash, and this is going to be the name of this Newman projection. So see what I did, the steps that I did. I changed that into my condensed form. This is kind of like a condensed form. It's still not completely condensed. We're going to call this either, it's between condensed and the structural because it still have the bonds in there. And then you choose the longest visual carbon chain. Whatever carbon chain you see, just go ahead and draw that because definitely this is not going to be your longest. After you draw it in a skeletal form, you're going to pick your longest carbon chain. You're going to number it according to IUPAC and then figure out the name.